When we imagine life beyond Earth, we often picture something like ourselves, carbon-based and water-dependent. But what if life could arise from entirely different building blocks? Today we'll explore the fascinating world of non-carbon-based life theories, where science meets imagination to expand our definition of what it means to be alive. In 1891, Julius Scheiner theorized about the possibility of silicon-based life. The main similarity with carbon and silicon is their ability to form four covalent bonds. Silicon is a strong contender for non-carbon-based life because of the diversity of silicon, making it theoretically suitable to support life. In 1908, Arrhenius proposed the panspermia theory, stating that microscopic spores were transported between planets through radiation pressures from the sun, making all terrestrial life on Earth having originated from extraterrestrial life elsewhere in the galaxy. The theory opens the possibility that life can exist in an environment extremely different from Earth's, and it reasons that non-carbon-based organisms could have also survived. In 1929, J.B.S. Haldane published The Origin of Life, describing his own theory about how life came to be. He said that the idea of a primordial soup, suggesting that inorganic substances, ultraviolet light, carbon dioxide, water, and ammonia, formed together in the Earth's oceans, and over time, through a series of chemical synthesis, were able to create complex organic molecules responsible for the first living cells. In 1954, Haldane stated that ammonia could potentially replace water as a building block of life. Ammonia, just like water, has a number of analogs and is a good solvent. However, the main downfall of ammonia is that it forms weaker hydrogen bonds than water, making scientists skeptical about how well it can hold complex systems. In 1962, Alex Fersoff builds on the ammonia life theory by stating that the first living organism on Earth existed in an environment with no free oxygen, but instead ammonia. That additive system of life formed based on ammonia would digest food utilizing ammonolysis, and instead of oxidizing food, they will combine it with nitrogen to produce cyanogen. This idea is plausible in theory, but it lacks concrete evidence of its existence. In 1998, NASA established its Astrobiology Institute with the mission to understand the origins of life both on and beyond Earth. NASA is recognizable on the world stage, so their research and endeavors feature prominently in the scientific realm. The program has the effect of promoting widespread scientific imagination about the possibility of other life. Continuing with NASA, in 2010, a group of NASA scientists claimed to have discovered a bacteria in a California lake that used arsenic as its main DNA component rather than phosphorus. The toxic effects of arsenic is already known, so it came as a big surprise to the scientific community that this is possible. The claims were later disproven, and it was found out that the bacteria were in fact phosphorus-based. The article was retracted, but the findings energized interest in astrobiology, and it forced scientists to reevaluate the flexibility of life chemistry. In 2016, a group of researchers presented that they were able to evolve bacterial enzyme using silicon. While they were able to isolate the bacteria and incorporate silicon into the hydrocarbon backbone, it's not particularly useful at this stage, but the enzymes were able to reproduce. These are the toeholds of the possibility of different non-carbon-based life research that's ongoing. In 2017, a NASA spacecraft, Cassini, revealed radar data that there were in fact methane-filled lakes on the surface of Titan, one of Jupiter's moons. Though the previous ventures have confirmed that methane lakes existed, Cassini demonstrated how vast the system is. Titan is the most concrete example of a potential life-supporting environment that exists without water. And if signs of life can be found on Titan, then the theory is that non-carbon-based life will transform into reality. In 2018, astrobiologists started exploring exoplanet biosignatures, which are measurable indicators that can suggest presence of life when combined with complex interpretation. Based on the results, the features of a planet can be determined and suggest potential biological activity. The model has only been able to successfully identify evidence of carbon-based life, but further application could reveal the existence of non-carbon-based life forms. With the growth in AI systems, they're playing a role in the simulation of non-carbon-based life. They can run simulations with alternate biochemistries and can decode complex molecular systems vastly different than that of Earth's. It also goes alongside biosignature modeling as it can analyze data sets effectively. It can also be parasynthetic biology to design and test life systems with hypothetical conditions. In 2019, NASA announced that a rotorcraft would launch in July 2028 and arrive in 2034, with the purpose of gaining concrete data on the different surface compositions as well as analyzing the habitability of the environments. The mission will confirm the existence of water-based or hydrocarbon-based life and the possibility of non-carbon-based life forms. From this visual timeline, we see how different non-carbon-based life theories build off of one another, with the ammonia-based life by Haldane leading to Axel's ammonia life theory, and even the panspermia theory and Haldane's theory about the origin of life contributing to both of those. NASA's astrobiology program was an important part of the later missions that occurred to tie in different spaces, and it was able to cement a concrete interest in non-carbon-based life theories. Thank you so much for joining me on this dive into non-carbon-based life theories, and I hope it's a topic that interests you and you'd want to explore deeper.